This is just going to be a quick talk through of the notes for law of sines. Law of sines is, when we can use it, it's going to make solving triangles significantly easier because the algebra involved with law of sines is less complicated than the algebra involved with law of cosines. So triangle congruence, if you think back to geometry, we learned about some angle and side configurations that taught us about congruence of triangles or didn't give us enough information for congruence of triangles. Now this is important because all of the congruence theorems, if we get that information, we can use either the law of sines or the law of cosines to solve the triangle. So last class we talked about side angle side and side side side, which I didn't really say that out loud, but that's what we were doing. Triangles, when we were given the information side angle side or information side side side, we could resolve for some of the missing pieces. With law of sines, we're going to be able to solve some more triangles if we're given angle angle side or angle side angle. Basically, if you're given at least two of the angles and one of the sides, you're going to be able to probably use the law of sines because of the math involved with it. Additionally, if we're given side side angle, which is one of the non-congruence combinations, we remember this because backwards it's a no-no word for school, but if you get side side angle, the law of sines is going to work still. However, we may have, it's called the ambiguous case, because we may have actually no triangles that can be made from this, or in fact two triangles that can be made from this, and we're just not really sure. So the law of, this says cosines, but LOL, it should say sines. The law of sines states that the ratio of the sine of an angle to the length of the opposite side is the same of all three angles of any triangle. It's an extension of the congruence theorem in Euclidean geometry, which is what we study. We study Euclidean geometry. So the theorem itself for law of sines is let triangle ABC be any triangle with sides and angles labeled in the usual way, which we discussed last time. Then we know that these proportions are true. Sine of angle A divided by side length A has to be proportional or equal to sine of angle B over B equal to the sine of angle C over side C. Now what these proportions are going to be able to let us do is they're going to be able to let us solve an angle side angle or an angle angle side triangle. So notice if we take what we were given here, which was two angles and a side, and when you draw it, it was angle, angle, side, right? Angle, angle, side, that's what we know. Well, we know both pieces of A. We know angle A and side length A. Because we know both pieces of A, we can set up proportions involving A and then the missing pieces of B and C to find B and C. Now, the reason that this works, and because we weren't really given either angle B or angle C, however, if you know two of the angles in a triangle, which we do in either case, you can find the third very easily, 180 minus the given angles. So all we have to do is set up two separate proportions. Sine of A over A equal to sine of B over B. Side length B is the only unknown here. Bloop, bloop, bloop. We're going to cross multiply and divide to find that side length B is 10.115. Then you set up a different proportion, this time still using sine of A over A because that's what was given. Obviously, you could use the B's now that you know B, but we'd have to round this, so it gets a little bit inaccurate. I like to stick with what we started with and setting that equal to the other proportion. We can cross multiply and divide to solve for C and get the side length for C. So if we're given side-side angle, for the most part, law of sines is going to work. It's just called the ambiguous case because we have to make sure that these measurements are actually going to make a triangle. So if you see here, we were given angle, side, side, or side-side angle. If we set up with what we know, which we know these both pieces of A and one piece of B, well, we know 3 of the 4 pieces of this proportion, so we can plug everything in and solve for angle B. Now what might happen with this is when you're doing this part right here, because of inverse sine needing to be in those first 2 quadrants, right, it's over here, between -1 and 1 for sine, that if you happen to be taking the inverse sine, that stuff happens to be greater than 1 or less than -1, then you're going to get an error and no such triangle can be created. That's why sometimes it's the ambiguous case. Just knowing the 3 measurements at the start is not enough to know that a triangle exists. But in this case, it ends up working out. We get angle B, which means very easily we can find C, 180 minus given A minus the B we just found. Now we have all 3 angles. Given, we found that first, and we just found that by subtracting 180. Then you can set up the last proportion. Again, I like to stay using the proportion they gave me. They gave me both parts of A. So when I cross multiply and divide, I don't have such a rounded number that I'm working with. So here's what it's going to look like when that ambiguous case actually has 2 triangles that can be made. Because of the way that this triangle is drawn with this 30 degrees, this side length being 7 and this side length being 6, we don't know if this connects, this distance of 6 connects with an acute angle for C and obtuse for B, or an obtuse for C and acute for B. We don't know that information. And honestly, that distance is going to reach either direction. So it's going to reach here and it's going to reach there. So we'll actually have to find 2 separate triangles. If you think back to our homework with law of cosines, we had an example where you had to find 2 separate triangles, and that algebra was bananas. You had to set up a quadratic and plot the zeros and plug those numbers in. This is the same kind of problem. However, the math involved with this, since it's still just proportions, is significantly easier. So I would lean on the law of sines when you're doing something like this. But the math itself, again, is just like the problem we did. So we'd have to solve case 1, where we find B, and then we need to find C in case B is obtuse. So we took 180 minus that acute angle B1 that we found to find the second option for B. It would be the supplementary angle to that first one. And then we can find the rest of the triangles. I won't personally give you a lot of examples of this, but these exist. So we always need to qualify our side angles. We got to be cautious with this one and just make sure that a triangle actually exists. And then we can get into some real world situations like this forest ranger, making sure that we understand the directions that they're giving us when it comes to like navigational directions. When it says 32 degrees east of north, well, north is always straight up. So if I'm going 32 degrees east, that's this angle. Or 48 degrees west of north, again, is the west direction from north, straight up, so that we can draw the correct pictures. But again, the math on this, super easy, just like that first example we did. You can laugh at my flames. Okay, last but not least, we have this road sloping application question. It really just wants the height of the telephone pole. The pre-cal part of this, super easy. All of this part, finding the different angles A, B, and C, comes from things you should remember about vertical angles, supplementary angles, and complementary angles from geometry. In fact, when I explained this in class, I think I actually used different explanation than you see here written on this page. So there's plenty of ways to arrive at angles A, B, and C using that information from geometry when you draw a really good picture. So make sure that your pictures are as accurate as possible to help you understand the question, because again, once we know each part, the law of sines is pretty easy math to do.